Hello, welcome everybody. It's really an honor to be here. Today I'm going to talk about some brain signals and how you stream your thoughts and everything that's in your brain to your console. Hence the name console.log brain, because that's the best way we debug applications, right? Maybe that could be a good way to debug your brain as well. So I'm Armagan Amcalar. I come from Berlin. I work for a company called UNU GmbH, and we're building electric scooters to unlock the urban life and the future of mobility. And I'm also a founder at a voluntary organization called Lonja, which is a software craftsmanship school for women, because we need that in the industry. I'm also pretty much active on GitHub. I have libraries that range from front-end frameworks to backend frameworks to microservices frameworks to platforms as a service to audio applications to brain signals applications. Pretty much everything I do is online and open source. So if you're interested in any of those topics, you can find something online. So last year I joined a meetup called Hack and Tell in Berlin, and it's a meetup where real-world hackers get together every month and present their best hacks. And at the end of the day, they vote on the presented hacks and choose one for the best hack of the month. And I was wondering, what is the ultimate hack that we can do? What is the ultimate hack that we can display that I can do in that meetup and hopefully win the trophy? And it turns out that it's about the brain. That is what we're after for many, many years. We want to unlock the potential, the true potential of our brains. If you followed the news last year, Elon Musk went into this business. He has a new company called Neuralink, I guess, and they are working on building a brain-computer interface, something like what you see in my head, an EEG device that is in your skull, that hopefully translates your thoughts or your brain signals into instructions that the machines can understand. And he's a little bit optimistic about everything. And he said, we're about 8 to 10 years away from this technology being realized, and people with disability will be able to use that. Right after that, I guess a couple of days after that event, Facebook had another event. They announced that they are also going into neuroscience and processing brain signals and helping people type with their brain signals so that you won't actually have to work with your fingers, your thumbs on your phones, and your phone will directly understand you, whatever you think, and you'll be able to tweet it or post it as a Facebook message. So this is Regina Dugan, a director of engineering, VP of engineering at Facebook. And this is a real slide. They're like, so what if you could type directly from your brain? That's a very, very good question, of course. It would be awesome, right? Would you like that? Raise your hands if you would. Yeah, of course. Everybody would like that, right? So this is a picture of me, if you couldn't tell already. This is from 8 years ago, 2010. This is my best friend helping out. And I have an EEG cab and a lot of electrodes. Doing my master's thesis, I had the opportunity to do a live broadcast where I could type with my brain signals. This is a tweet from 2010. I did this with my brain signals. I typed it with my brain signals. The URL of the tweet, actually, if you go to that URL, I guess right now it points to my research. But so 8 years ago, or 8.5 years ago, this was a thing. And we had it in the academia. We had a brain-computer interface that let you type with your brain signals. So it's nothing new. But where are we after all these years, in 8 years? I'm sorry to say it, but there has not been much progress on the field. That's why we need a lot more developers and a lot more hand to make this a reality. But the thing is, yeah, this was a thing back then. In 8 years, there was not so much progress on it. And in 8 to 10 years, I guess we'll be at a similar similar place. So you still have a lot of time to learn neuroscience, get into this, use your programming skills. And I'm actually here to tell you that with your current programming skills, you can actually be a part of this revolution and make a change. But before we move forward, a little bit introduction on EEG, electroencephalography, and brain signals in general. This is an image from 1924. It's been captured by a German researcher whose name is Hans Berger. I know that's a very generic German name, but it's not made up. That's his real name, Hans Berger. He had this crazy idea that he could capture signals out of the brain and diagnose some patients with that, with the signals that he captured. Of course, this is a very, very low resolution device out there. You don't really see much quality signals. But the idea was that, he said, this is a theory. I'm going to grab these signals. I'm going to grab these from sick people whom you kind of burnt as witches. They're not witches. They just have mental problems. And I'm going to prove to you that you can track this with electrical activity. And he was a very respected, well-respected scientist back in the day. But when he published this paper, he was kind of shunned out of the academia. Nobody believed him. Everybody called him a charlatan, that it's not possible to get electrical signals out of the brain. Like, you cannot do that, ever. Almost 10 years later, other people tried his research, and they said, well, you know what? This actually works, and it's a thing. So they kind of gave his reputation back. But it was a huge challenge. So this is really, really tough. It doesn't work all the time. It doesn't work as you expect. And back then, the devices were just very, very low quality. So of course, he was called a charlatan. But nowadays, we have a lot more quality equipment, and we can amplify signals a lot better. And this is how it looks right now in kind of like this device as well. It looks like noise. Anybody knows what noise is? Noise signal? Yeah. So it's like that thing that you hear at the end of soundtracks or something. So this is pretty much noise. This is affected by all the electrical signals around you. It's affected by your cell phone, by wireless networks, by the electricity, the main line, and the brain signals that you produce are on the order of microvolts. That is 1/1,000,000th of a volt. And if you consider that a single battery is like 1.5 volts, it's very low to detect and to amplify. And therefore, it's also very, very hard to deal with this. But people kept on experimenting. And in 1988, they came up with something called an Oddball Paradigm. It's an experiment where researchers tried to help people type with their brain signals. It was 30 years ago. And they did. They were successful. So I'm going to show you a run in a minute. But the goal was to basically help patients or people with disability to be able to communicate, because it's actually very important. If you have no other means of communication, if you can't even move your muscles, or if you can't even blink on your own, this is really important. If you can communicate, if you have a pain, or if you are in need of medication. And they were able to achieve 2.3 liters per minute in 1988. So what you'll see is it is hopefully a video. Let me see. OK. Well, oh, yeah, there we go. Perfect. So this is me sitting at home trying this experiment in 2017, late 2017, 30 years after the original, which is a re-implementation of my master's thesis in JavaScript. But the idea is there are letters on the screen. There's a matrix of letters that range from A to Z and then 0 to 9. And what you do is you have to sit very quiet. You cannot move. You have to stare at the screen. I'm trying to type hello in this video. And I'm focusing on the letter H. And then the computer just does a lot of machine learning in the background from my brain signals. And it shows me the letter that I want to type. So the next letter is E. So I'm counting the E's whenever they flash. So 1, 2, 3. So I'm counting internally, let's say, whenever they flash. And this is called the Oddball Paradigm. The E's, the letters that I want to type, are relatively rare with respect to the other letters. And whenever I see that letter and whenever I count it, there is a special signal in the brain called P300, which occurs 300 milliseconds after you get that flash, after you get that get that stimulus. And I'm like, yes, this is the letter that I want to type. And that special signal occurs in the brain, and we track that. Basically, we record brain signals in real time, and then again, run some machine learning algorithms, classification algorithms, to figure out what we want to type. And the next letter will be L. So it's a pretty boring watch because I cannot do anything else. I cannot move. If I move, the muscles in my body, the muscles on my head, like my jaw muscles or any other muscles that I have, will interfere with the signals, with the brain signals. So the results will not be as good. I will not get high-quality signals. So I basically cannot do anything else. I cannot even open my mouth because the signals will go crazy. And the thing is, this is a consumer-grade hardware. So the problem is that if the electrodes move on your head a little bit, and they do when you move your head, then you also lose the signal. So it's not really useful for real-world stuff, but it's fun for toys. And if you have research-grade tools, then you can help disabled people, of course. We also had some experiments with disabled people to see if they could use the system, and some of them could. So in academia, this thing works. In the lab, it works. In real life, it doesn't, or kind of does. So we are kind of getting to the end. Let me skip forward a little bit. Yeah. And then I see hello. Thank you. That was a huge relief for me, because I'm kind of suffering from the imposter syndrome. Does anybody know what imposter syndrome is? Yeah, I think most of us have it. And I'm like, I was accusing myself of leaving academia, of not continuing this research, and I went into web development, and I thought I lost my edge. But then 8 years afterwards, I could prove to myself that, yeah, I can do stuff again. I'm not that apart from that brain research, from that neuroscience. I can still do it. And this time, everything is in JavaScript. So it's a huge challenge. Back then, we were using MATLAB, C++, and C# for coming up with all sorts of machine learning algorithms and the UI. But right now, everything is in JavaScript. So that is actually the point of the talk, that you can do these things with JavaScript. So where do you start? There is a library called wits that I open sourced on GitHub. So if you have this headset, it really hurts, by the way. It's like drilling in your head to get the signals out of it. If you have this headset, you can install wits, and the code reads very nicely. It's like constant mind requires wits. Then you do mind open your mind, and then you do mind.read, read your mind to the console, and it just basically logs some numbers to the console. It's not as fancy. You just get a lot of numbers, and then the rest is up to you to run your machine learning algorithms to make something useful out of those numbers. It gives you 128 samples per second from 14 different electrodes. So whatever you want to do with those electrodes, you can. And this basically was the idea was that we let people type with their brain signals. OK. Then, for more fun, I wrote something called a brain monitor. That is a CLI application. It's not a UI application. It's a CLI application. So you don't need a GUI for that. You can run it in your terminal. But it streams your brain signals in real time. It's just an npm package, again, you install and you use this brain monitor. And it gives you the battery and all the electrodes and something called a gyro. Anybody knows what a gyro is? An accelerometer? So it basically tracks the movement of your head. In case your brain signals are not enough, you can make use of the sensors of the accelerometer and basically use that to do more signal processing, if you like. And this basically is a monitor that also shows you that gyro. OK. So the original source code for this, the demo that I showed you, it's also open source and online. So you can also download that and play with it. If you're interested in brain signals or helping out, help is much appreciated. It's open source for a reason, so that we continue to develop it. It's not only development work. There's also a lot of UX work here. If you notice, the letters have covers, colorful colors here, covers here. Instead of flashing letters, we are covering the letters. Because the idea is we have to surprise the patient. And the more you surprise them, the better the signals are. So I'm experimenting with different colors and different paradigms of making this work. And this is a little bit under-researched in the academia. What can we try to do with this matrix? Or can we try different forms and different shapes? And basically, you can help there as well as an application designer, for example. Again, everything is implemented in JavaScript all the way up. We have native C add-ons for the headset. If you know already, you can write native C code in JavaScript and compile them so that you can require them and use them in JavaScript. So this headset doesn't really give you raw data. It's actually also encrypted. So some nice people on GitHub reverse engineered it and made it open source. And it was available in C, so I wrote wrappers for it for Node.js so that you can stream data to Node.js. And then I use Electron as a wrapper so that I bring Node.js and the browser together. And I use Vue.js on the front end. Did you like the Vue talk, by the way? That was before this? Raise your hands if you did it. Yeah, it was a very nice talk. So Vue.js is a really nice framework. And I'm using that. I actually kind of learned Vue.js with this project. And it's using something called Brain.js for neural networks. It has a neural network as a classifier, and then something called a BLDA. It's Bayesian linear discriminant analysis. It's another technique that some people developed with MATLAB, and then I basically transformed into JavaScript. I don't recommend it to anybody. Don't try it at home. It's a horrible experience to translate MATLAB code into JavaScript. One line in MATLAB is like 100 lines in JavaScript. But people claim that you cannot do scientific computation and calculation in JavaScript, right? Well, it turns out that you can. You can do neuroscience. You can do brain research and help people type with their brain signals. So it's at least that good. And there are a lot of libraries for doing that. A lot of libraries that do linear algebra in JavaScript. Some of them use WebGL, so your code actually runs a lot faster than computational software. But I couldn't find any library that could calculate the eigenvector which is a very, very special, very unique, non-deterministic calculation. So what I did was I used MATLAB for that. And I spun up a web server in MATLAB, which is an environment, a language for scientific computation calculations. But it also runs Java, so you can put a web server inside MATLAB. So kind of the roles have changed. You know, JavaScript, which was primarily used for web applications and web servers, is now used for scientific calculation. MATLAB, which is primarily used for scientific calculation, is now used as a web server. And I have one single function there, the eigenvector function. I pass it an array of values, and it basically computes the eigenvector and sends it back. It's the only thing that I'm using in MATLAB. And it basically boosts the accuracy. But yeah, that was actually very fun. So how we process the data. We get the raw electrode data that's 90% noise, so we have to filter that. We filter the frequencies between 1 and 12 hertz, and we kind of divide the signal into 1 second epochs. So after every flash of a letter, we record 1 second of brain signals, so that we look for that peak at 300 milliseconds. If you remember, the wave is called P300. There's a positive peak at the 300 millisecond mark, so we're looking for that. We do a lot of fancy named stuff, normalization, winsorizing data to clip them, to remove the blinks and stuff. We leave out the samples that we're not interested in, and then apply machine learning, Brain.js for neural networks, and again, a custom algorithm in JavaScript. So, oh yeah. So this is kind of the machine learning task. The red ones are the average values of what we get when there are no surprising events that we are interested in. You know, if I want to type H, the red ones are the signals you get when the other letters are flashing. And the black one are the signals that you receive when H is flashing. So if you see, here is a peak after 300 milliseconds. And this is what we're trying to differentiate. Is it a red line or a black line? Obviously, these are averages of like 20 runs, which means they are already pretty much purified. The individual samples that you get are not as clear as this. I mean, the distinction is not as clear. And also, you make mistakes, because there are randomly flashing stuff around. Sometimes your eye focuses on other letters. And in the end, it's a very, very hard machine learning task. And there are not so many features in the signal that you can extract and make. So now, before I jump to the conclusion, let me show you something else. Oh, this is the brain monitor, by the way. OK. As I told you before, this thing is a consumer-grade hardware. I'm kind of having spotty connection right now between my brain signals, between my brain and the computer. So this demo may not work, so please bear with me if it doesn't. Any Star Wars fans out here? All right. Does anybody remember this scene? I guess it's from the second movie, kind of one of the opening scenes. Luke Skywalker is basically strangled in a cave, and there's a Wampa in that cave, and he tries to save himself. He's stuck, and his lightsaber is over there. He tries to reach for that, but he cannot. And he needs to use the Force to get that. Now, I wrote a video player in JavaScript for this demo, to be able to do this demo. Because apparently, none of the web APIs that deal with video allow you to reverse or rewind the video. You can only play forward, you can pause it, but there's no way to rewind the video. So I made a custom video player, and it's also open source online. The repo's name is use the force Luke. And now if I can use the force, if the force is strong with me, the video will play forward. If it's not, it will stop or go back or rewind. Now, I did this demo 2 days ago in another conference, and it went like crazy straight ahead. And the effect couldn't really be seen. I'm not sure how it's gonna play out right now, or even if it's ever gonna play out. So bear with me when we try. I guess it's not working. The force is not strong with me today. Thank you. So we couldn't save him. Or did we? Let's see. I'm not going to try again. But I'm kind of on the good side. So I don't want to leave him hanging there, upside down. Blood rushes to your brain. It's not the best experience. So let's let him have the lightsaber. Yay. He saved himself, chopped the arm off the Wampa, so now he's free. Yay. Thank you. OK. So the conclusion. People kept saying that JavaScript is powerful enough to read and parse JSON APIs. And I claim that it's not only good for that, but it's only good for parsing your brain's API. And I kind of try to provide you the tools to get started. So now the question is, will you join the revolution? Thank you. Thank you for watching me today.